this video, we will compare two database systems, Dynamo and Cassandra, and direct your attention to some points that you should keep in mind while deciding on which database to use for your application.
Dynamo is offered by Amazon.com as part of the Amazon Web Services portfolio. This means that the deployment options of Dynamo are quite limited. Also, it is only used by Amazon's internal services. Its operation environment is assumed to be non-hostile and there are no security-related requirements. By contrast with Dynamo, Cassandra is an open-source database management system, which supports multiple deployment options. Customers can run Cassandra on-premise or any cloud platform. Docker containers are also a possibility.
Cassandra inherited its decentralized architecture from Dynamo. Both database systems are implemented in Java. One architectural difference that we would like to mention here is that Dynamo Database Local Persistent Store is a pluggable system, where you can select storage depending upon the application use. Generally, Dynamo Database uses Berkeley Database or MySQL. Cassandra's storage engine isn't pluggable, though there were some successful attempts to replace it. For example, Instagram has implemented its own storage engine on top of Rock's database, named Roxandra, to reduce Cassandra's tail latencies. And this worked out well. Nevertheless, for now, replacing storage engine in Cassandra requires special effort. For more information, have a look at Apache issues. We left a link on the slide.
Dynamo's data model is quite simple, represented by binary objects identified by a key. If the application deals with unstructured data, Dynamo would be a better choice. Quite the opposite, Cassandra was developed primarily for structured data, which is stored as a multi-dimensional sorted map and allows applications to access their data using multiple attributes. This data model was borrowed from Google's Big Table.
Both observed database systems use consistent hashing for data partitioning. The consistent hashing algorithm presents some challenges. The random position assignment of each node on the ring leads to non-uniform data and load distribution. Also, the algorithm is oblivious to the heterogeneity in the performance of nodes. Typically, there exist two ways to address this issue. One is for nodes to get assigned to multiple positions on the ring. Here the concept of virtual nodes is used. The advantages of this approach are, firstly, if a node becomes unavailable, the load handled by this node is evenly dispersed across all the other remaining nodes on the ring. Secondly, when a node becomes available again, or a new node comes to the system, the newly available node accepts a roughly equivalent amount of load from each of other nodes on the ring. Finally, the number of virtual nodes that a node is responsible for can be decided based on its capacity. The other approach is to analyze load information on the ring and have lightly loaded nodes move on the ring to alleviate heavily loaded nodes. The Cassandra opts for this approach because it makes implementation very tractable and helps to make very deterministic choices about load balancing.
For application, Dynamo uses the algorithm that the Cassandra terminology is called rec-unaware. It replicates keys at the replication factor -1 clockwise successors of a coordinate node in the ring. However, the algorithm is modified to assure that replicas are stored in different data centers. Cassandra offers a richer set of data replication strategies. In addition to the clockwise approach, Cassandra allows to use a Zookeeper system for application.
For bootstrapping and membership tracking, Dynamo and Cassandra use the same techniques: seed nodes and gossip protocol. Temporary failures are handled using hinted handoff. It is a common strategy in write-path to handle and repair temporary failures in systems with leaderless replication. In read-path, the approach for handling temporary failures could be either strict or sloppy quorum. Sloppy quorum in Dynamo means that hinted replicas stored in nodes other than replicas count towards read consistency requirements, thus improving read availability. Cassandra does not use hinted writes this way.
An important design consideration is to decide when to perform the process of resolving update conflicts, i.e., whether conflicts should be resolved during reads or writes. Dynamo and Cassandra target the design space of an always writable data store, pushing the complexity of conflict resolution to the reads in order to ensure that writes are never rejected. The common heuristics for conflict resolution are vector clocks, which are used in Dynamo, or last write wins, implemented in Cassandra. Last write wins is a simplification over the vector clock approach. It could lead to potential data loss. However, the maintainers of Cassandra believe this simplification is justified because the data model is different from a key value database.
Consistency in Dynamo is facilitated by object versioning. When a client wishes to update an object, it must specify which version it is updating. This is done by passing the context obtained from previous read operation. This means that the write operation in Dynamo also requires a read to be performed for managing vector timestamps. This can be very limited in environments with higher write throughput. Both database systems use anti-entropy Merkle trees for data recovery. The key difference in Cassandra's implementation is that Merkle trees are built per column family, and they are not maintained for longer than it takes to send them to neighboring nodes. On the other hand, Dynamo uses persistent on-disk hash trees instead of in-memory ones. The advantages of this approach, as stated by its maintainers, are twofold. Firstly, ability to run anti-entropy operations with the minimal impact on memory usage. Secondly, nodes can be restarted without a need to rebuild hash trees. According to the CAP theorem, both Dynamo and Cassandra are AP systems. The difference is in their approach to consistency. Dynamo provides eventual consistency, which allows for updates to be propagated to all the nodes asynchronously, while Cassandra enables users to choose between synchronous or asynchronous writing. The former corresponds to the parameter all. Thus, Cassandra is deemed to provide tunable consistency.
So, when should you use both? For example, in heavy write workload conditions. Nevertheless, also suited when fast reading is required, or for application over multiple data centers, and always on apps. And now, when should you use neither of them? For example, when complex queries and joins are required, or in asset-dependent systems, for instance, core banking systems, handling bank transfers. In fact, no NoSQL technology will perform there well. Such systems need relational databases. Also not suited in systems that need strong consistency. Cassandra has a measure to remedy it, but it's not enough for precision-demanding solutions. Finally, when lots of scans are required, Cassandra and Dynamo read data pretty well as long as you know the primary key of data you want. If you don't, they will have to scan all nodes to find what you need, which will of course take a while. So when shouldn't you use either of them? Cassandra is not good at handling lots of updates and deletes. Cassandra is incredible at writes, but it's only append-oriented. Dynamo targets applications that need to store binary items that are relatively small, but is not generally suited to store documents or images. A better architectural pattern for this implementation is to store pointers to Amazon S3 objects in the DynamoDB table.